All right, so this is section 5.1, and we will talk about length and dot product in Rn. First of all, the definition of length might be familiar from physics classes or Calc 3, or any time you computed the dot product, the distance between vectors. But this is just to clarify the notation. We're going to use the notation for the magnitude of v with these double bars. And to compute the magnitude of v, take the square root of each component squared. So let's see a theorem about it. Let's say we wanted to compute the magnitude or the length of the vector c times v, where c is a scalar. So let's see what happens when you multiply a vector by a scalar. This theorem states that you may as well just find the magnitude of v and then multiply it by the absolute value of your scalar. So let's see how it works in general. So in general, because this is a course about proofwriting, I have to reiterate this continuously. When you prove an identity, you want to start with one side and work your way out to the other side. So first of all, this tells us to multiply on the inside of the magnitude symbol. It says to multiply c times v. So technically we have to find the magnitude of c times v would be c multiplying every component there. So it'd be c times v1, comma c v2, and so on, c vn. So we're finding the magnitude of this vector. Now, according to this formula, to find the magnitude of this vector, we have to take the square root of each of its components. So we're going to have to go ahead and take the square root of cv1 squared plus cv2 squared plus cvn squared. And to do that, we can distribute the square to each thing in the radical there. So that's c squared v1 squared, c squared v2 squared, c squared vn squared. All right, so now you see that this sum has a common factor of c squared. So we take the common factor out, and we have v1 squared, v2 squared, vn squared. Square root of c squared is the absolute value of c. In other words, if this constant is a -2, when you take the square root of -2 squared, you're going to get a +2, right? So when you take this out of the radical, you got to make sure you turn it positive. And then we all know that from the definition here, we see that the square root of v1 squared, v2 squared, vn squared is really just the magnitude of v. So we showed that when you take the magnitude of a constant times a vector, it's really just enough to multiply the magnitude of the vector by its absolute value. So following, there's a lot of computations in this section, and the homework is mostly computational, so there's not much else there. Some definitions you might already know. U is special notation for the unit vector, and to compute a unit vector in the direction of v, we're going to divide v by the magnitude of v. So that gives you u, which is a vector of magnitude 1 in the direction of v. So we also need to talk about the distance between two vectors, and this is going to be a big deal in this chapter, in chapter 5, and then it comes back with chapter 6 and linear transformations. So the distance between two vectors, it's the magnitude of u minus v. And we can put a little spin on that soon. So we can't really talk about distance without dot product. So we look at the dot product of u and v in general, of course you already know this probably, the dot product of u and v is given by multiplying the corresponding components, so u1 times v1, u2 times v2, un times vn, and then adding the product. So you start with two vectors in Rn, and the result is a scalar. So you end up with not a vector anymore. That is now a scalar. All right. So let's look at some examples. This problem, let's say we're given two vectors in R3. Let's see if we can find a bunch of things and how the numbers fall into place. If you were to find the